Dan, for the introduction. Hello, everyone. I'm excited to be talking today about the future of robotic manipulation. And then towards the second half of my presentation, I'll talk about how we do that with ROS and MoveIt. And so let's jump in. The first question I want to start with are, where are all the robot arms? A investment friend of mine recently pointed out that the best kind of robotic company is one that can get rid of the robot. And so before I talk about robot arms and the rest of this presentation, just want to back out the question, do we need them? In the case of things like burger making, it's questionable. In the left picture here, we see Flippy, where they are making robots similar to how they're making burgers similar to how humans do it, requires less retrofitting of a kitchen. It's more compelling, perhaps, it's exciting, but on the right, we see another startup in San Francisco called Creator, who's doing robotic burger making as well, but more assembly style. And it does basically the same outcome. Similarly, in San Francisco Airport, you may have seen Cafe X. They have a robot barista to make you coffee, but we've had coffee vending machines for decades. And while the quality may not be as high, I bet we could fix that if we put our minds to it. So perhaps robot arms aren't always needed, and that's why um, we haven't seen them all the time in our lives. But I would still expect that in our normal day-to-day lives, we would come across in this day and age in 2020 robot arms more often. And unless you work in a factory or a car manufacturing plant, you may never see robot arms on a day-to-day basis. But the dream's always been there, and it still is. And I think we're on the threshold of something big, seeing robot arms really explode in investment and in commercial activity beyond manufacturing. So the dream is this multi-purpose robot, and that's when I think robot arms are appropriate, is when you have a multitude of tasks that the robot can adapt to and do things alongside humans, not having to change the environment much, not have to change your kitchen, your home, your office. Um, and so in the picture here, we see the famous PR2 robot, popular or built by Willow Garage. It was the original robot built for ROS, which I'll talk about later about what ROS is, the robotic operating system. And this is essentially the promise of Rosie the robot from the Jetsons in 1962 when that cartoon first aired. We've been dreaming of this for a long time. And what you see in these pictures of dishes and cooking and laundry, this isn't commercially available yet, or it barely is. This is mostly pictures from research groups and labs. So let's not get too excited, but I think we're on the cusp of that. So before I talk about the future, just a quick background of where we've been. In 1961, we saw the first industrial arms being used in manufacturing plants. That's a full 60 years ago now. And teach pendants were the dominant way of programming them. There's been incremental progress ever since then, such as PC-based control. And the biggest thing in robotic arms in recent years, all the buzz, is cobots. Marketers love the term cobots. And what that means, in case you're not an expert in this area, is the robot's safe enough to work alongside humans. So you could have a human doing a task and the robot assisting them, or the human take over, or the robot take over, and the forces and torques and other aspects of the robot behavior is such that it's safe for an average worker to work alongside. But there's still been a lot promised with cobots that haven't fully come to fruition. The other thing about cobots is that they don't require a safety cage and e-stop, the same kind of e-stop circuits and such. So where robot arms really have dominated is large-scale manufacturing. So this is a Tesla plant, but really every car manufacturer, that's still where the number one place where robot arms are sold, and all sorts of other manufacturing. More recently, what's happening today, what's really exciting right now, is in terms of robotic investment for robotic arms. So self-driving cars were huge a few years ago, and other sorts of AI, but right now the warehouse logistics space is blowing up. And I think a lot of this is because of Amazon and how they're dominating this industry of next day shipping, 2-day shipping, and all these other companies are trying to catch up, such as Berkshire Grey, Right Hand Robotics, Kindred. They're all doing types of mixed package, mixed parcel sorting where you have to sort between different products and fulfill them for different orders. It's a lot harder problem than a conveyor belt of the same exact product, but rather you have this large mixture, and it takes a lot more AI and perception and sensing to achieve these. What we're on the cusp of, I said tomorrow in this slide, maybe it's tonight, but Mobile manipulation is the next big thing, combining all these autonomous vehicles with robot arms. And so a number of companies are going after this right now. IAM is one of the more traditional ones, the robot arm tacked to a base. NVIDIA doesn't really have a robot arm, so barely belongs in this talk, but I think it's pretty clever how they use a combination of suction and a mechanical system and a scissor lift to move boxes off shelves. And finally, the gorilla in the room, of course, is Boston Dynamics, popularized by all their great demo videos. And here, they've now turned their eye towards a commercial application of warehouse logistics. Other companies are also coming to the front, like Bastion. And so the market size for all of this is huge. Basically, the task that humans do with the two appendages on their body, we do so much with our hands and our arms. And as robot arms become more capable, they will be able to do essentially all of those things. So because this is robo business, I wanted to provide some concrete numbers, but this global robotic arm market is forecasted to basically double by 2024 and to 40 billion. And even the collaborative robotic space is exploding in this graph here. So there's just a lot of money and attention being paid right now to this. But the question is like, how do we still get these robot arms out of the factory? There's some limited success right now, but it still really hasn't taken off. Particularly like, where is our Rosie the robot? So I personally have my career has been about robotics and arms, and my dream has always been to have a robot that can do things like laundry and setting the table. And so how can we get robots beyond these highly structured factory environments, even warehouse environments, into other commercial spaces and other medical spaces and consumer spaces like the home? Um, so there's a few things, and what I call them here are these next-gen robot manipulation capabilities, these advanced capabilities. Even Boston Dynamics has done some pretty advanced stuff, but when you look beyond the demo videos, there's still a lot of shortcuts they're taking and a lot of blind spots in their capabilities. So I want to present to you in this talk these 5 things that are preventing us, and that's the costs, the software capabilities themselves, things around safety, mobility, and standards. So in terms of hardware costs, the harmonic drive pictured here is the bread and butter of most robotic arms today, or at least for collaborative robot arms. There are many other mechanical systems for controlling robot arms, hydraulics and whatnot, but let's just start with this example. This piece of equipment, it has a lot of tight tolerances that are expensive to manufacture. And so in order to get the precision and accuracy that manufacturing applications demand, this is a requirement. But if we could make smarter software that can compensate for things like mechanical noise and backlash in your robot arms, then we could presumably make cheaper software. And so things that would accomplish that are closed loop control, where you take sensors and you have quicker feedback, other things like visual servoing. So an example of this is if you are listening right now and you have something in front of you that's a fixed object, reach your hand out full, straight. Don't touch anything, but put your finger very close to an object. Maybe it's your laptop right now. Maybe it's the dashboard of a car you're driving right now. Well, if you're driving, be careful. But notice how if you put your finger very close to an object and you focus on it, your finger's kind of shaking and it can't exactly hold its position. Now, an industrial robot arm, these traditional beefy arms, they can be super precise where you can not really notice any shake or any jitter. But our human arms, we don't have very precise manipulators. Our arms are noisy, and that's okay. We're extremely versatile. Humans are very dexterous and can do a lot of great stuff. And so presumably our robots should be able to do the same thing for these everyday robots in non-manufacturing spaces. So we know it's possible. We just need smarter software. Another thing is economies of scale. This is a typical argument for when you can drop the price on something. There are not a lot of like killer apps right now where robots have really blown up, or any particular robotic company is really blown up outside of these factories and warehouses. When it does, though, we'll see prices plummet. So if we could attach a robot arm to every cell phone that's manufactured today, we would see prices drop. That's totally impractical and makes no sense, but you get the example. So the next point of what's holding us back are these software capabilities. I just talked about how we need these closed loop control, but there's other things that are difficult for robots to do outside of structured environments. So things like partial occlusions. In this picture here, you see it's a very cluttered environment, and maybe you want to grab the salt shaker, but it's covered by another cup or pot. The robot has to reason about how to grab something behind something else, and that takes a lot of extra computation to plan this non-linear motion. On the perception side, when something's partially covered, it's a lot harder to recognize than if you have the full visual of the object is. If you can only see the top piece, top part of a salt shaker, it might be more confusing for a computer system to recognize. And then finally, this unpredictable situations. It just takes a lot more state machines and decision matrices of how to predict these different situations and how to compensate for them. A lot of more error states to accomplish for. In self-driving cars, we've had the technology to do self-driving cars for a long time, but getting all those unpredictable situations of bikers and pedestrians just jumping out in front of cars all the time, that's taken a lot of engineering and ingenuity to accomplish, and we're still seeing that being worked on today. And we'll see the same thing as robot arms become are released into more common spaces. And that brings me on to safety. Speaking of jumping out in front of cars, don't do that. So these consumer applications, like these hypothetical robots in your home, they face a whole new slew of difficulties that we haven't seen in factories. You have these non-professionals who aren't being trained, who maybe aren't as alert because they feel safer in their normal offices or environments. So, for example, we haven't dealt as researchers in robotics or developers of robotics applications, children playing on a robot, but a robot arm has all sorts of pinch points that could potentially hurt a child, and that would be terrible and a giant liability issue. So have to worry about that, or even other unpredictable things like curious pets. I've never seen a video where a cat jumped on a robot and covered it up and gave the robot a hard time to reason about what to do, but it's bound to happen one day. And then finally, there's trade-offs. So cobots, one of the things that they've done to make them human safe is to simply slow down the velocity, the momentum that these pieces of mass have so that they can't harm a human. But if you have a robot that's too slow for safety reasons, it really doesn't become very useful. If you ask your robot to set the table, but it takes it 10 minutes, your food's going to be cold and you won't be happy with this robot. You won't buy it. So it's a trade-off, and we need to come up with more clever ways of reasoning about the environment for safety concerns. Um, One thing that robot arms are typically limited is that, well, typically they're bolted to the floor or to a table. And so their workspace is only that which their 6, 7 degrees of freedom can reach around them. And so we have to worry about how do we get a robot to have a larger workspace so we can do more tasks? Because if you're bolted to a table, there's only so much you can reach, and you can't go across the room and do something else that might be useful to a human. So of course we need to have these mobile manipulators that have wheels or legs. But then a whole other set of problems occurs. First, costs go up because you have a lot more hardware to deal with. The complexity goes up because now calibrating your robot arm, its location in space, is made more complex because it moves. Another thing is in a lot of homes and even commercial places, you'll see tough thresholds for wheels to drive over, or steps, a step you have up, or even worse, staircases. A lot of commercial buildings do have elevators, but not all. So if you don't have an elevator, it makes it very difficult. The common workaround for this is legs, but legs are even more expensive in terms of hardware cost, in terms of the danger of it losing balance and falling over. The same kind of problems that we've seen with the Roomba and the iRobot as pictured here. Um, and then finally, the last point is standardization. And this is really a big push of the rest of my talk is how do we standardize all these components that must be put together to make versatile Rosie type robots to get these next generation manipulation. Right now, as it stands, every manufacturer of arms, they have their own custom interface. And this is for lots of historical reasons, but I did some research for this talk, and I knew about some of these scripting languages, but I was actually shocked about just how many. I got tired of putting together. But you see in this box, all these different scripting languages for FANUC, ABB, KUKA, Kawasaki. The list goes on. And then on top of that, you have your standards like Python, C++, Lisp. And so it's difficult, if not impossible, for one person to know how to use all these different types. And what that creates is vendor lock-in. Once you build a system for one type of arm, it becomes hard to transfer that application to a different arm. And that reduces price competition. So Now I want to talk about why current solutions do not address this Rosie problem. And there's two areas I want to focus on. One is off-the-shelf hardware, and the other is on the software side. So on the hardware side, um, most hardware is shipped with programming environments that are too restrictive for a lot more advanced applications. Now, there's benefit to this because they're very focused. They're really good at doing a few things, and perhaps they're really easy to do those few things, which makes it better for non-experts. But if you are an expert user, you're developing your own robot product. I presume if you're at RoboBusiness, you're probably interested or you are involved in making your own robot product or using robots in novel ways for your company's needs. And so these hardware companies, their application capabilities are limited. Another point of why their application capabilities might be limited is that these companies are really good at making hardware that's robust, and their core competency might be in the manufacturing and supply chain and precision of that. And that's great. But I think I personally have a theory that it's hard for a company to be really good at both hardware and software. There's a few exceptions, like Apple has been good at both, but most tech companies stick to software. And when they've tried to venture into hardware, let's say Google, for example, there's been a number of failures. Um, so yeah, so you have these hardware, and then one thing that they do when they are selling their hardware is that they provide software with APIs that are crippled. And so that's another problem here, is that they limit what you can do. And the reason they do that is they're afraid of being commoditized. If they become just hardware providers and they don't provide any premium differentiation from other robot arm companies, then they know they'll be commoditized. They can't charge a premium. It's just a difficult space for them. And that's understandable, that's rational, that's business. But for the desires of next generation robot arms and applications, I don't think that's very beneficial for the rest of us. And so the way they cripple these APIs are things like limited control rate. Ask any researcher. The frequency at which you send commands to the robot is sometimes artificially low. Maybe you can command it at 30 hertz when really you need it to command at 1,000 hertz to get some really high performance applications. The scripting interfaces are poor. They're just old languages with limited flexibility. And finally, the dynamic models is something that it's the model of the inertias and masses of the robot. And the companies manufacturing the robots, they don't want to give those out because that might be part of their IP. That might, they think, give away too much of their secret sauce of how they build the arm. But what it does, it makes it for third-party developers, it makes it really hard for them to make applications that can be performant compared to the built-in things that come with the software. And so as a researcher, that's an important piece. And then something I find particularly egregious is that I've seen some manufacturers of robot arms actually have license agreements that say that if you're using their API and you're not using their easy interface software, but the more advanced mode, you can use it for research use only. And if you want to use it as a commercial application, either you can't or you have to get special permission and licensing from the supplier. Then on the software side, there's a lot of software out there with varying degrees of complexity and feature sets that are designed to work with different types of robot arms and solve a lot of the problems that I'm complaining about right now. You see a list here: Acton, Kineo, Robot Studio, RoboGuide. A lot of the manufacturers like ABB and Fanuc provide their own. But they still have similar issues, I'd argue. They still tend to sacrifice developer flexibility and advanced capabilities in exchange for the needs of doing a few applications really well, like typical manufacturing things like welding that car companies need, or painting. And they make it easy for a non-expert user to use, but make it more crippled for a company who wants to make their own robot product to use. And finally, they're not always the most modularized or component based, so you can't take them as building blocks to build new applications. And so that would be what I argue is the deficit of a lot of these frameworks. And so to sum up what I've just talked about, there's this trade-off going on between what manufacturers of arms have done is they've looked at where the biggest buyers are. It's still in manufacturing and it's still in auto industry, and they've optimized for industrial reliability and robustness. Two things that are crazy important when you have a factory running for 10 years, 24/7. Those things are important. And they have a lot of people who are non-experts who want to be able to reprogram and adjust things as new products come in. So they've optimized for non-experts. But this has sacrificed the possibility for developer flexibility, for advanced capabilities, and the need of experts. So that's kind of, I mean, I'm definitely simplifying all this and taking some shortcuts in the way I'm describing all this, but that to me is the general thrust of what is frustrating about robots today, robot arms today. And I've heard this resonate from a lot of our clients at PickNik and a lot of researchers I've talked to and other people who I've shared these thoughts with. And so, in sum, I would argue that this is an innovation hindering environment. There's a lot of great things going on in robotic arm manipulation, but there are some issues here as well if you're trying to build non-industrial robotic arm applications. So you have to balance three things, and it's a very tricky thing to balance. So if you want to make a robot to make burritos today, let's just say burritos, for example, you'll have to make custom software that solves fundamental, like low-level algorithms for robots, like inverse kinematics and things that are out of textbooks that have been done a million times before. You'll have to also build custom software because all the reasons I just described. You may come to the decision that, oh, we can make it cheaper and we can avoid all these API issues, and so you have to set up your own supply chain and do all the robustness testing that required in making hardware. Very big endeavor. And all the while, doing these two things, you have to also focus on what your actually end user needs and wants. So if you're making burritos, what's the temperature of the burrito going to be? How do they want it delivered? Like what's the best flavor profile? These things that don't even matter about the robot algorithms. You just want to be able to take those and focus on your like the secret sauce of whatever company Robot for X is that you're focusing on. So um, the ARC, an alternative approach. I was going to get here eventually, I was going to say it, but I think that a lot of the solutions to the problems I've outlined are open source robotics. This is a much more collaborative environment that will cause more innovation so that we can finally get to that Rosie the robot that we all dream of, or most of us dream of. And so this innovation limiting environment would be solved better if we had more open standards in robotics. Robotics is a young field, so it's understandable that we haven't established a lot of great standards yet. But open source is a great way to make huge strides there. And we already have. Open source has been around for quite a while now in robotics. It would help with interoperability so that you can avoid vendor lock-in, better collaboration between academics and researchers and commercial companies and R&D labs and corporations, and really just avoid reinventing the wheel. And on the collaboration point, there's a lot of hard problems that aren't solved yet in robotics that we can't just like assume that we can take what exists and then like close your eyes to innovation, but um, there's still fundamental problems that are preventing us from solving this Rosie problem. So the logo down here, ROS, the robotic operating system, I'm sure almost all of you have heard of this if you're tuning in today for my talk, but maybe you only heard about it a little bit, so I'm going to give some background. But this was started in 2008 at Stanford and at Willow Garage and has really taken the robotics industry by storm. It's got a lot of momentum. The Willow Garage's thesis about why ROS matters is that essentially creating truly robust general purpose robot software is hard. It's so hard that no single individual, laboratory, institution, or I'd argue even company can hope to do it on their own. So we have to work together in order to get this future of manipulation that we're dreaming of. So why should you pay attention to ROS? One, the biggest one, costs, of course. As a business person, we always want to reduce R&D costs and reduce the risk. So most everything in the ROS ecosystem comes with very business-friendly licensing. It's very rare for it not to. And what that means is that it's not copyleft. And if you build derivative work on top of it, you're free to keep that closed source and not contribute any of it back. Not a lawyer, but it's a great thing. And second, you can hire talent easier. Another common pitching point is that all these undergraduate programs and graduate programs, PhDs, they're all publishing work and learning in school. They're learning ROS, and so when you're going to hire talent, they will be pre-trained if you're on a standard that everyone's using. I mentioned earlier that there's a lot of open problems in robotics, and so this tech transfer is very important. It's been going on for a decade now. There's been so much published on it. I'll get to that in a minute. Finally, ROS is industry standard, but it's built on another, even older industry standard called DDS. If you know what that is, I'm sure you're excited to hear that. So when I say it's standardizing on ROS, there is a lot of momentum here from big names, big players. Recently, the technical steering committee was established by Open Robotics, the company behind ROS, and there's 14 companies currently. Some of the biggest names I've put on this slide, you can see Intel, Amazon, Microsoft, Toyota. And so you see all these big corporations standardizing because they see the value in this, and I hope you do too after this talk. There's been several consortia established to help further bring ROS into various industries. ROS Industrial is focused on the traditional manufacturing space. They have a huge consortium of members. We're a member as well. The AutoWare Foundation is another one focused on self-driving cars. They've taken ROS and added the sauce on top of it needed to focus on that application. And I represent personally the MoveIt community, which is another focus area of ROS for robotic arms and manipulators, which I'll be talking about in just in a few slides. And our community is very vibrant, and I encourage you to get involved. So to bring this back to the earlier half of this talk, how is ROS helping us achieve the next level of robotic capabilities? On the hardware cost front, the commoditization of hardware is to our benefit, unless you're an ARM manufacturer. And even then, I would argue that if we see more applications using ARMs, you'll see more sales. And so I don't think it's that a big deal. Software capabilities, this is there's more software basically because it's open and there's a huge amount of software that you can download today for free, and you can build on Giant so that you can take the top crust that you're making, the secret sauce of your application, and build on top of all these other components that already exist to save you time. Robot mobility is actually a key feature of ROS. It's one of its strongest suits is this navigation stack that's been around for a long time. A lot of companies have built on top of that already. And out of the box, you basically get the ability to drive around and localize and make a map of your environment. Huge value out of ROS. And finally, ROS is basically a big framework of standards. It's a middleware for message passing between different programs and nodes, they call it. And these are all defined by messages that are standard interfaces. And so a lot of standards in robotics have been coming out of ROS. And it's an exciting place to be, seeing that robotics invented. I mentioned earlier just a little bit more about ROS. Hundreds of startups have used it. There's been 7,006 research papers cited to date on ROS, and hundreds of millions of dollars of company valuation, such as Fetch Robotics. The CEO, Melanie Wise, she was one of the actual original creators of ROS before she started Fetch. This company has since raised $94 million based on that PR2 robot that I showed you at the beginning of my presentation. They've basically evolved that to what you see in this picture. And then to be fair, open source is maybe not always appropriate. So to give a well-rounded talk, if you have low customization requirements, if you're not building a robot product yourself, you're just trying to automate a factory that makes paperclip widgets, maybe you don't need to have something as complex as and flexible as ROS or open source robotics in general. If you don't care about owning any robotics IP and you'd rather just license it out from another integrator or robotics company, maybe you don't bother with ROS, although I'd argue the companies you're licensing from are using ROS under the hood, most of them. And finally, if you don't have an expert development team, you don't want to pay those high San Francisco salaries or PhD salaries, maybe ROS isn't for you, but there's developers all over the world using ROS that doesn't require those high salaries I just mentioned. A common concern I hear when talking to our clients is their intellectual property and this concept, this myth really that bringing in open source can somehow hurt your patents or your IP. And as long as you're not doing copyleft and check with your lawyer, make sure you read the licenses. But ROS almost never has that. Then you're pretty much in the clear here. And really, your competitive advantage shouldn't be these building blocks that can be found readily in robotics textbooks. You don't want to rebuild the same things over and over. It's just kind of a waste of time and money. Your innovation should be taking these components and composing them for a particular application, like the burritos I mentioned, and not focusing on reinventing the wheel. So As promised, I wanted to touch on MoveIt. That's the thing that I'm particularly passionate about. Kind of I based my PhD on, and then now this company on this open source MoveIt platform. And basically, MoveIt is a very popular, one of the most popular apps in ROS. So in this ROS ecosystem, there's several sub ecosystems, MoveIt being one of them. We focus on robot arms, which is the whole thrust of this talk. And I like to call it a hardened motion planning platform because we've been around for a while and we've been refining it for a long time. The first version was actually called Arm Navigation, and it started about the same time that ROS started in 2010. There was a full rewrite to make it a lot more powerful and flexible, and that was rebranded to MoveIt in 2013. We didn't officially take it out of beta 1. Like pre 1.0 until last year, just as a courtesy. We were like, yeah, it's really stable. We should send the message out that it's like super ready to be built on. So we gave it the 1.0 label, a very common thing in open source robotics or open source software. And I'm particularly excited about MoveIt 2.0, which we've kicked off this year. I'll get to that slide in a minute, but it was first released last February, and we had another release this February, and another one coming up soon. So what is MoveIt? It's a set of different capabilities that you can mix and match to make your own custom applications. It's very modular, it's plugin based, and it's advanced motion planning, meaning that it doesn't just interpolate straight between A to B, but it actually can plan around things. So an example of this, if you have a robot opening a refrigerator door, you have to grab the handle, pull it open, and then when you release the handle, you can't just move into the fridge. There's a door in the way. You have to have an algorithm and some kind of software reasoning to tell you to move your arm out of the way of the door and then back into the fridge itself to grab whatever ingredient, right? And so that requires things like collision checking, where you have a model, a virtual model of the environment, and then the robot reasons about how to not hit things. And you combine that with 3D perception so that you can create that model using depth cameras, RGB cameras. And then other things that MoveIt provides are manipulation and grasping. How do you grab the handle? Where do you grab it? What angle do you grab it at? And finally, control. That's the low-level drivers that command your actuators, like PID loops. It's a whole ecosystem of components in MoveIt. A lot of different research groups have contributed their work to it, and so you can mix and match the components that make sense for your application, which makes it very extensible. You can even make your own custom ones if there's a particular piece that doesn't suit your needs. So MoveIt 2 is based on ROS 2, and just a quick recap on ROS 2. The community is very excited about this right now because unlike ROS 1, which was designed for more academia, it has been used in lots of industrial purposes, but originally designed for academia. ROS 2 is designed for industry from the get-go. It's designed for commercial applications, meaning that you can prototype with ROS 2, and then when you go to market, you don't have to like rip ROS 2 out and then replace with something else. It's production ready. A big request we've had from users is not just to support Linux, which is what ROS 1 did, but really have first-class support for Windows and Mac OS, and that's available now. And what I'm going to talk about next in my last few slides is real-time capabilities. Real-time is a big deal for MoveIt and something that wasn't available in ROS 1. So real-time, why care about real-time motion planning? Well, to get these advanced motion planning things that I've been kind of hinting at throughout this talk, you need really responsive and fast software. You need guarantees about when you send a message to a different process, how soon it's going to get there. And this will allow more complex interactions of using forces and torques. Those types of data, force and torques, they expire really quickly. When you have dynamics being planned for, you've got to be very fast in your reactions. You can do things like dragging, pushing, smoothing, wiping, scraping. Traditional applications have mostly focused on pick and place, like just picking something up, but this is a much more complex. And so it'll also enable closed loop control, reactive control, and very high rates of streaming commands, up to 1,000 hertz or many thousands of hertz. So just a quick primer on what is real time. It's a loaded word, but hard real time generally means it's fast enough for safety critical systems. Cobots, for example, if your buffer overruns and you miss a command, the arm could jerk in an unexpected way and hurt someone, and it's very dangerous. And soft real time is when if it misses a message or some of its timing, maybe it fails to do something like grasp an object, but it's not a big deal. It can just regrasp, retry. And so hard real time, you need the computer system you're using to have a lot of uh, very defined deterministic behavior. You can't have it just suddenly start lagging because of some background process ran. There's different types of middleware. I'm going to skip past this, run out of time here, but in the MoveIt 1.0 architecture, we've already done recently some big strides to improve the real-time capabilities of MoveIt. And so if you are a MoveIt user and you haven't heard of MoveIt CPP, check out the tutorial online. It's open source. Check it out today. But we've basically moved some of the latency delays that was introduced by using ROS1 so that you have more access to core MoveIt components. And this has a lot of benefits that we're very excited about in the MoveIt project. But in MoveIt 2.0, we're redoing the architecture, and this is work that's in progress and scheduled on our roadmap, but we're using ROS2's component nodes so that optionally all of the different pieces can communicate with shared memory in a much faster real-time manner. So we have multiple threads separating out the application from MoveIt planning to the low-level controller. And then finally, hybrid motion planning is another big piece in the MoveIt 2 roadmap that I encourage you to check out. Rather than just doing global planning or local planning, we're doing a clever combination of switching between sampling global planners and local planners. And there's a lot of pros and cons to both these approaches. So global planning allows you to plan around those complex obstacles like refrigerators that I mentioned. And it doesn't get stuck in local minimum, but the cons is that it's a lot slower and you can't really, given current computer abilities, you can't really plan in real time and it's not deterministic. With local planning, which is more inverse kinematics, Jacobian based, this is the more traditional thing that you see industrial manipulators use. It's very fast, deterministic, reactive, but it just can't do as many complex things, and it's harder to do collision checking with it. And so we're working on this hybrid planning approach, which can have multiple threads at different rates. So let's say 30 hertz and 300 hertz, for example. So different speeds of planning that allows you to simultaneously plan locally and globally to get the best of both worlds. And some example applications where this is helpful for is human-robot collaboration, painting a wall, filling a dishwasher, or even complex things like balancing a tray while placing on a table at the same time. So just a roadmap about MoveIt 2. I kind of hinted at this earlier, but we've had our alpha release, we've had our beta release, and coming pretty soon, hopefully in this July, we'll have our official release, which will be targeting the ROS2 Foxy version. Right now we're in Eloquent, pictured here, but they're coming out next month and with the next version of ROS, and we'll be coming out with the next version of MoveIt to complement it. So you can actually download MoveIt 1.0 today. You can download MoveIt 2.0 today, the beta version. It's all online at moveit.ros.org/install. I encourage you to check it out. Like, there's no salesperson you have to go through. Um, it's got a vibrant community around it. Our roadmap's on our website too, but a quick screenshot of it. These are some of the milestones. I don't have time to go through all the details beyond the real time, but we'll be doing more things like leveraging more of the ROS2 capabilities, and then in the future, improving the planners to be more deterministic, adding more out-of-the-box state machines and user interfaces. And finally, machine learning's proving to solve all sorts of hard problems in the past, and we're using it for grasping, but using it even more and more in the MoveIt framework. If you are interested in learning more about MoveIt, we have these yearly events. Our 5th annual World MoveIt Day is actually, I think, in 2 weeks. June 2nd is World MoveIt Day. It's a annual hackathon. This year there will be no in-person events, obviously, but it's all the more. It's super easy to just like log in from wherever you are. There'll be a video feed. We'll be super active on GitHub. We'll be on IRC. And it's a great chance for you to get you and your coworkers or your lab to join us remotely and kind of get started. It's a great place for beginners to start learning MoveIt or for you to help us improving the project. And then another big event, we'll have our 2nd annual MoveItCon this year in November. It'll be co-located with ROSCON in New Orleans or perhaps virtual, but that's November 17th, another great chance to get involved in the MoveIt project and take advantage of it. This is our website. There's lots of information. I encourage you to check it out. And before I go, just want to mention a little bit more about PickNik. We're a R&D shop. We love doing custom software, helping you build that on top of open source, meaning that if we didn't use open source, it would take X amount of time to build some big application. But with open source, with MoveIt, with the tools that we're really experts and familiar at, we can do that in a fraction of the time. So please reach out to us if you're interested. We love de-risking open source and using strategy and expert advice on how to develop custom robot software. So that's my talk. I really appreciate your time today. Check us out on Twitter for more information. Our URL is on the slide, picknik.ai. Again, I'm Dave. It's been a pleasure talking to you about some of my theories about where robot industry is going. In particular, how do we get past manufacturing only? Like we've been in that for 60 years, but I really want to see in my lifetime robot arms in our offices, in our small businesses, at home, at consumer locations doing all sorts of cool things, and not just like in a gimmicky way, like making coffee when a vending machine can already do that, but in more advanced, impressive ways that can do like multiple things at once. I think we're closer there. I think open source is a big key to solving that, to getting past that hurdle. And I hope you can get value out of MoveIt. It's free software you can start using today. And thank you for your time. And also, I think we have time for a few questions. If anyone has any questions, please take them.